let's talk about the Schrodinger equation. Let's, in our numbering system here, this is the sixth postulate. So postulate number 6, the Schrodinger equation. The state function, psi, okay, evolves over time. Remember we said psi is a function of coordinates and time, right? So this postulate says that the state function evolves over time, so it changes with time, okay, according to this equation. This is called the time-dependent Schrodinger equation. So it must obey this equation. So what is this equation? This is I h bar derivative, partial derivative of psi with respect to time is equal to h hat psi. And what is h hat? That's your Hamiltonian operator. That's the operator corresponding to the sum of the kinetic energy operator and the potential energy operator. Okay, so that's one equation, one of the most basic equations that you need to know by heart. Okay, so that's your time-dependent Schrodinger equation. Now, we're going to focus on what are known as stationary states, which we'll get in cases where the Hamiltonian operator, or more specifically the potential energy part of the Hamiltonian operator, is independent of time. If you remember, what's a kinetic energy operator? Negative h bar squared over 2m, right? And then the sum of second derivatives, right? Derivative with respect to x, derivative with respect to y, derivative with respect to z, second derivative with respect to z. This is for a one-particle system, right? So you can see there is no time dependence in your kinetic energy operator. Okay, so the part of the Hamiltonian operator that could depend on time is the potential energy. Now, if that potential energy part does not depend on time, then it's possible to have what are known as stationary states. Okay? So, if your Hamiltonian is independent of time, then you can show that there are solutions to your Schrodinger equation that can be written in this form. Not all solutions can be written in this form, but there are solutions. There's a set of solutions that you can write in this form right here. And what do we mean by this form? Wave function, your state function is a function of coordinates and time, right? Now, we can write that if you have a stationary state is defined as one that can be written as a function of coordinate times a function of time. We say that coordinates and time are separable. You can separate these two variables, basically. Okay? So, not every function can be written as a function of coordinates times a function of time. Let me just illustrate that with something very simple, not necessarily there. Let's say I have something like x squared plus x plus 1 times 2t. See, you can see that's a function of x times a function of time, right? But if I were to write something like xt squared plus x squared t, can I write that as something that just depends on x and something that just depends on y? Okay, let's see if we can factor out xt, and what do we have? T plus x. Can you separate that? Something that depends on time, something that depends on x? No, right? So we're going to be interested in cases where we can write our wave function as a function of coordinates, function of x, y, and z, times a function of time. Okay? Those types of wave functions are called stationary states. Right. So, let's go back here. So, there are solutions to your Schrodinger equation that can be written this way. And if that is the case, it's very easy to show that the part that depends on time is just this expression right here. E to the negative I et over h bar. So this is e to the negative I et over h bar, where e is a constant. Okay? And this e right here It's the same concept you get if you apply the Hamiltonian on little psi. Make the distinction here. This is capital Psi, okay? Function of coordinates and time. We're writing it as a function only of coordinates, so the part that depends only on coordinates, we're using lowercase psi. So uppercase psi, lowercase psi, right? So when you put that, that becomes uppercase, okay? So anyway, this E turns out to be the eigenvalue of the Hamiltonian operator. So we can identify E then as the energy. If we measure the energy of that system, and it happens to be in a stationary state, okay, we're going to get a well-defined energy. So in other words, a stationary state is one that has a well-defined energy, where your wave function is an eigenfunction of your Hamiltonian operator. We can also show in this particular case that H hat big psi is equal to E times big psi. Okay, so stationary states are states that they are described by a wave function which is associated with a well-defined energy. These are wave functions that you can write as a function of coordinates times a function of time, and the function of time is written this way. Okay? Now this H hat psi equals E psi is what we'll be using throughout the rest, pretty much the rest of the course, because we already know the part that depends on time. We're only going to be looking at stationary states. Okay? And you might ask, why not make it general? Well, because Hamiltonian is a Hermitian operator, right? So any other state you can just write as a linear combination of the stationary states. So if you have, like I said, if you have a stationary state, if I put an SS here for stationary state, those stationary states are eigenfunctions of the Hamiltonian operator. So they form a complete set. So any other state function, any other psi, can just be written as a linear combination of these stationary states. So why are we interested in stationary states? If we leave the system alone, we'll have a constant well-defined energy. Okay, so these are systems with well-defined energy. And ultimately, that allows us to, by solving these stationary states, we determine what the allowed energies are for the system. And why are we interested in knowing what the allowed energies are for the system? Because we can verify the validity of our theoretical predictions, the predictions of quantum mechanics, by spectroscopy. Remember, delta E, the Bohr frequency condition. The change in the energy of a system is equal to h times the frequency of the photon that is either absorbed or released when it undergoes that energy change. So spectroscopy then is the experimental verification on the predictions of quantum mechanics. Okay? So we're going to look at those. We're going to look at some very simple systems, and then for your next test, and then after that we're going to look at atoms and molecules.